the theater of magic.
I love pinball. The sights, the sounds, the physical nature of actual stuff happening in front of you, and not just on a video screen, have long appealed to me. In fact, for as long as I can remember. Of course, a big draw to me is that these machines are, well, machines, and wondrous machines at that. A pinball machine is a fascinating tribute to humanity. Artists, musicians, game designers, and even voice actors work alongside machinists, fabricators, craftspeople, and engineers to manufacture these elaborate contraptions made purely for our amusement. Well, and to gobble up our quarters. With so much going on inside one of these, even just sitting idle, you might have wondered how they work. Luckily, somebody gave me the keys to this machine so we can look inside. It's a computer. There's a computer in here. It keeps track of where the ball is, shows you your score on this display, plays music and sound effects through speakers, and lights up all the various light bulbs when they need to be lit. How very modern. But pinball goes back much further than this. And not even 20 years prior to this machine leaving the factory, pinball machines didn't feature any integrated circuits of any kind. This is Aztec by Williams. Built in 1976, this machine hails from the tail end of the electromechanical era. It wouldn't be long before manufacturers started tinkering with electronic controls. In fact, 10 copies of this very game were built as prototypes for the Williams System 2 microprocessor unit. This one, though, well, it's a little more old school. And today, I'm going to show you what makes it tick. Seriously, why is it ticking? To find out, we'll have to look inside. This time it opens from the back, and once you remove this panel, you won't see anything that looks like a computer. In fact, you'll find an unholy mess of wires linking quite the assortment of oddball assemblies together. And this isn't even the half of it. Inside the main cabinet under the playfield, there's even more. We get in there by opening the coin door, pulling this lever which releases the lockdown bar, that's this large metal piece at the front edge of the cabinet. Then once we remove the lockdown bar by lifting up on it, we can slide the glass out and the playfield will simply lift right up. There's even a handy prop rod. Now that we're in, we see even more wires and even more stuff. And that's not even the whole of it. Some of the control mechanisms are attached to the underside of the playfield. Each and every one of these devices is critical for the function and logic of this game. While this is nowhere near as complex as Theater of Magic, there's still a lot going on. There's a full-on rule set and series of goals in this game. Different targets light the letters A, Z, T, E, and C. Light them all up and there's a chance for an extra ball. There's a bonus added for hitting certain targets, which is awarded at the end of each ball. And if you hit the right targets, you can double the bonus value. There's more too. If you complete Aztec and fill the bonus ladder up to 50,000 points, that lights a special, which awards a free game. And which out lane is lit will flip back and forth as you hit other targets. You can also win replays based on your score, and that's configurable. Some of the rules can even be changed. Winning a special can award an extra ball instead of a replay, and there are even 3 difficulty settings which change how many targets need to be hit before other opportunities are awarded. But aside from rules and features, the machine also needs to keep track of which ball is in play, and thus how far you are along the game. Oh, and by the way, you can choose whether you want 3 balls per game or 5. It has to end the game when it's over and disable the playfield, and when a new one is started, it needs to reset the scores to 0. Plus, up to 4 people can play this game. It's fun to compete. So it needs to keep track of which player is up and only change that player's score when it's their turn. Somehow, that's all being accomplished with this rat's nest of wires and stuff. How? Why, it's easy. Just look at this schematic. I'm sure you can figure it out. I'm kidding, of course, and even if you studied this for hours, it's not going to make any sense unless you understand what these parts are doing and how they work together. So, since you're all watching, I suppose it's my job to explain what these parts are doing and how they work together. We'll start with the basics and work our way up. And we're going to go way back to basics with a bit of history. But just a bit, I promise. Pinball is called pinball because in the earliest days it was a simple game of balls and pins. An evolution of the French game bagatelle, early games were very simple. Marbles rolled down a board set at an angle with pins nailed into the face. Those pins would create obstacles that deflected the motion of the rolling balls, and would often form goals worth points. Games like this were made going back to the 18th century, but they would remain obscure toys for the wealthy for many years. Then, sometime around the Great Depression, some clever folks devised ways to automate the game and turn it into a machine, albeit a very simple one. David Gottlieb designed Baffle Ball in 1931, which is widely regarded as the first commercially successful pinball game. I don't have one to show you, but I do have Microsoft Pinball Arcade. Baffle Ball was a simple, baseball-themed, I guess, marble game with the twist of being coin-operated. When the coin slide was pushed in, trap doors in the goals would open, allowing the balls to fall down into the machine and collect at the ball shooter. Then the player had their fun. These early games were purely mechanical, featured manual scoring, were meant to go atop a table or other such surface, and started showing up in bars and parlors all across the country. And plenty of gambling based on your score occurred too, but that's a story for a different time. Baffle Ball was so successful that it spawned plenty of imitators, such as Ballyhoo, which, by the way, was so successful that the company that produced it would rename itself Bally. With a variety of games for players to choose from, companies making pinball machines scrambled to add new features in order to make theirs stand out. Features like bumpers, electric lights, automatic scoring, and eventually movable bumpers in the player's control. It was none other than D. Gottlieb and Company that introduced electromechanical flippers in 1947's Humpty Dumpty. While the arrangement of the flippers on the playfield is certainly odd by modern tastes, this machine set new and enduring standards for pinball. And 29 years later, one of Gottlieb's main rivals, Williams, would release this machine, Aztec, the one I'm standing behind and that this video is principally about. That one. First, let's look at what the player sees. The playfield is still just a wooden board with things attached to it that a ball rolls around on. But now a variety of targets, obstacles, bumpers, plenty of lights, and let's not forget flippers, make the game fast-paced, visually interesting, and addictive. As with most pinball machines, the playfield is slightly off-center, as the right-hand side of the machine is taken up by the shooter lane. That sends the ball up to the top of the playfield using a player-operated plunger, just like the earliest games. A simple gauge is printed on the shooter to help the player hit the ball with consistent force. Depending on the game's design, the strength of the initial plunge may be important, and many games feature a deliberate element known as a skill shot, where extra points are awarded if you get the plunge strength just right. Now you'll notice that there are fairly large obstacles which block off parts of the playfield. This is done mainly to define paths the ball might, or in some cases must, take. These can be created in a number of ways, but the most common is plastic posts fastened to the playfield, which are then fitted with rubber rings. Large rings may be stretched across 2 or more posts to create a linear barrier, but you'll find plenty of individual posts with their own rings too. The rubber rings make the ball bounce off these obstacles, often unpredictably, and some of the larger barriers will award 10 points when hit. To fill the otherwise blank areas of the playfield created by the obstacles, decorative plastic pieces printed with graphics matching the game's theme are placed atop the posts. This also helps visually define the shape of the off-limits areas. Underneath the plastics, you'll find small incandescent light bulbs. This is the only safe place to put them since the ball can't hit them, and they illuminate the playfield to allow for play in a dark room. All things considered, this is a pretty simple layout with a small number and variety of targets. Aside from the various 10-point bumpers, this game features 3 rollover buttons, 8 rollover lanes, 6 stand-up targets, 1 spinning target, 1 kickback lane, 2 slingshot kickers, and 3 pop bumpers, though Williams would prefer you call them jet bumpers for trademark reasons. All of these award points when they're hit, but they often do something else too, or change how many points they award. But for now, let's just focus on the points. The game shows you your score on the back glass with these mechanical readouts called score reels. Oh, by the way, this back glass isn't in very good shape, but I've got a reproduction replacement. I've just not gotten around to ordering the right piece of glass for it yet. Anyway, see if you can spot a fun little trick manufacturers were doing around this time. Look at the front, and now the back. Do you see what's off? Look at the front again. There are 6 digits in the score, but look at the back, and there are only 5 score reels per player. The last digit of the readout is in fact fake, and is only there to inflate the score. But Williams went through the trouble of printing the bottom of the 9 and the top of the 1 on the dummy reel, which makes it quite convincing. Here's a spare score reel, or drum unit as Williams calls it, we can look at up close. It's a fairly simple device, just a large plastic drum with the digits 0 through 9 printed on its edge, and a ratcheting mechanism to advance the position of the drum by 1/10 of a rotation. A small solenoid, a type of electromagnet, pulls on a plunger when electric current runs through it, and that advances the mechanism by 1 step. By the way, I hope you like electromagnets, because this machine is chock full of them. The game's circuitry runs on 24 volts AC, produced by this lump of a transformer sitting in the bottom, which also produces 6 volts for all the lamps. All of the targets the ball can hit that award points are merely simple switches. When the game is on and in play, those switches become wired to the scoring mechanism. Take these 100-point rollover buttons, for example. They literally are buttons, and beneath the playfield, 2 electrical contacts become pressed together when the button is depressed by the weight of the ball. You might guess that these 100-point buttons are wired to the score reel in the hundreds position, and sure enough, when I press it, that reel advances by 1 step. But that's not all that happened. A bell rang at the same time. Sitting in the cabinet near the coin door is the chime unit. This is a unit with chimes. Each of its 3 chimes has a solenoid sitting below it, and when power is sent to the coil, it flings a plunger up into the chime, which gives it a right smack. That certainly rings a bell. Since 2 solenoids were fired with 1 switch, solenoids that draw a lot of current and are located in 2 very different places, the switch on the playfield isn't what's powering them. Instead, the playfield switch powers a relay, specifically the 100-point relay, which lives in the back box. Relays are switches that are actuated with, wait for it, an electromagnet. A coil of wire creates a magnetic field when it's energized, which pulls on an armature, and that in turn actuates a series of switches. Sometimes relays are simple, and sometimes they're not. In pinball machines like this, they're not. Pinball pushes relays to their conceptual limit, using them to create the game logic and do countless other tasks. But that's a big part of why I like these machines so much. Notice that some of these switches are normally open and the contacts close when the relay is energized, but some of them are just the opposite. There's even a third option, make-break switches. We'll see some of those later. In this case, the switch on the playfield, since it was worth 100 points, completed a circuit to energize the 100-point relay. When that pulled on its armature, these 2 switch contacts closed, which completed a circuit both to the hundreds position score reel and the small chime. All of the targets worth 100 points have their switches wired in parallel, so that they'll all activate this relay when hit. And all that arcing we see is precisely why the game uses a relay and not the switches on the playfield. Seems simple enough, But there are many more switches on this relay than just the 2 that bump the score reel and chime. In fact, there are 6. One of these additional switches is there to ensure the score reel actually moves. Solenoids are fast, but they're not instantaneous. If the ball just brushes up against a target, the contact time may have been too brief for the solenoid in the score reel to pull completely on the plunger and actually advance it to the next number. So these 2 contacts actually provide a way for the relay to power itself. If I bridge them with a screwdriver, you'll see it pull in. On its own, this would be useless. The moment any 100-point target were hit, the relay would lock itself on and be stuck. But that circuit path travels through a switch on the score reel called the end of stroke switch. This is normally closed, allowing power to flow through, but opens once the solenoid has reached the end of its travel. At that point, it breaks the circuit powering the relay, so the relay lets go. Here's what that looks like on the schematic for the machine. Full disclosure, I've made some alterations to this and hidden a fair bit because some of what's visible here is very confusing without context I haven't given you yet, and it's not important right now. When reading the schematic, power flows across the page, and a circuit is active when there's a complete path from the left to the right, though it's AC, so it flows in both directions. The 100-point relay coil is right here. It will become energized when any of these switches close. They're labeled to indicate what and where they are, and sure enough, those are things worth 100 points. But this switch is labeled 100-point relay. That means it's a switch within that relay, and the symbol means it's a normally open switch. So it closes when the relay energizes, and since it also provides power to the relay coil, it provides that bypass, which keeps the coil energized even when input from the other switches is lost. But that switch is itself wired in series with all of these normally closed switches on the score reels. Those are the end of stroke switches we were just looking at. So once the solenoid on whichever reel it's trying to fire has actually fired, the relay will lose that bypass signal and de-energize. Another contact in the relay has to do with the number 9. The score reels are not mechanically linked. Each one operates entirely independently of the others. But if you have 900 points and score an additional 100, according to the laws of math, you'll have 1,000, so 2 reels have to move in order to display that sum. They do. And did you notice that 2 bells rang this time? This switch in the 100-point relay will actually cause the 1,000-point relay to energize as well, but only when the 100-point score reel is on the number 9. Look back at the score reel and you'll find a stack of switches, which we call a switch stack, oddly enough, sitting near the top. This switch is normally open, but a pivoting mechanism actuates the switch stack at the 9 position and closes that switch. When it's closed, an interlock is created between the 100-point relay and the 1,000-point relay. Take a look at the schematic again. These are the 9th position switches on the score reels, and you'll see that they connect to that switch within the 100-point relay. If the score reel switch on the player that's up is closed, meaning the 100-point score reel is showing a 9, then the next time the 100-point relay fires, power will also get sent through to this switch and up to the 1,000-point relay coil. Therefore, the 2 relays will fire together. All of the succeeding score reels have this interlock, so a score of 99,990 will correctly roll to 100,000 when a single 10-point bumper is hit. Speaking of the 10-point bumpers, now's a good time to go over the various target types on the playfield. When a rubber ring is stretched across 2 posts, so long as the distance is sufficient, a switch will be tucked behind that ring. The contacts are slightly separated, but will get pushed together when the ball stretches the ring, sending power to the 10-point relay, which advances the 10-point score reel, rings a bell, and also steps the number match units. Don't worry about that yet. There's a lot going on in here. The stand-up targets throughout the playfield are essentially the same thing as all the 10-point bumpers, but one of the switch contacts is attached to the face of the target. The gap between the contacts here is important. A wider gap will require the ball to hit the target with more force in order for that hit to register. But if they're too close, simply brushing against the target will register as a hit. So it's generally best to be somewhere in the middle. The rollover lanes are essentially the same thing as the rollover buttons, but instead of a button, a formed piece of wire sticks up through a slot in the playfield. When that wire is depressed by the ball, switch contacts below the playfield are pushed together, which adds the points. Generally, the ball can travel over these in either direction, but you'll notice that the designers had an evil streak with the out lanes. Those have their tripwires formed such that it will only allow the ball to travel down towards the drain. Should you happen to get very lucky and have the ball bounce off the apron and roll up the out lane, which does happen occasionally, unless it's going very fast, it will just bonk into this and fall back down. Boo! The spinning target, while very different in its execution, is similar to the rollover lanes. The metal plate that the ball hits is attached to an eccentric axle, I guess, and a wire linkage connected to the right-hand side goes below the playfield through a small hole. When the target rotates, that linkage is repeatedly pulled up and down, which in turn pulls on a leaf switch, repeatedly connecting and disconnecting the two contacts as it spins. When this target is hit just right, it's quite the show. But not quite the show that the jet bumpers can put on. Pioneered by Williams in 1948, these jet bumpers repel the ball at high speed when they're hit. They're triggered by a circular platform known as the skirt. This is attached to a stick resting in a bowl below the playfield. While rather silly at first glance, this arrangement means that no matter where the ball should hit the skirt, the stick will pivot, which in turn pushes the bowl downward, thereby pushing these two switch contacts together. That provides power to the solenoid beneath the playfield, which pulls down on this angled metal ring that floats above the skirt. When that occurs, the ball finds itself between that ring and the skirt. Solenoids are quite fast, so the ring immediately comes crashing down and makes contact with the ball. Since the ring is angled at roughly 45 degrees, the ball gets flung away from the bumper. This is a very rough process, and since the playfield is made of wood, a mylar protective sheet is installed around the bumper to minimize damage. This wasn't always standard practice though, so many older games exhibit severe wear around the bumpers. If you noticed the second switch down below the jet bumper, that is what actually registers points. It's just like the targets we've been looking at, but hidden away and activated by the movement of the bumper ring and not the ball itself. Not all games work like this though. Sometimes a pop bumper relay is used, activated by the skirt, which locks on in a similar fashion to the points relays we looked at earlier. A contact within that pop bumper relay awards points, and this switch serves as an end of stroke switch to release the relay after the bumper has fired. That approach has pros and cons, and Williams opted to power the solenoid directly from the bumper skirt switch. The main downside of this approach is that occasionally the ball will just brush against the bumper, so it kinda sorta half fires and it doesn't award points. And finally, we have the slingshots. These dastardly things are hardly a target worth hitting, as they only score 10 points, and they have a nasty habit of flinging the ball right into the out lanes. They're made up of 3 posts arranged in a triangle with a large rubber ring stretched across all 3. In the center of the long edge is a kicker just behind the rubber ring. The kicker is flanked on either side by 2 switch contacts. When the ball hits the rubber ring and either of those switches close, power is sent to a solenoid below, which pushes the kicker outward, stretching the rubber ring and flinging the ball away. Just like the pop bumpers, it's a switch below the playfield that actually registers points when the kicker has moved, and the switches behind the rubber only provide power to the solenoid. Oh, right, I forgot about the kickback lane here. This thing is sort of a combo of the slingshot kicker and a rollover lane. The ball lands on a tripwire, and after points are awarded, a solenoid below the playfield fires, which bonks the ball back up. An interesting twist with this machine is that the pop bumpers and the slingshot solenoids are provided with DC power. A bridge rectifier and capacitor are attached to the underside of the playfield, which means that there is in fact a single semiconductor in this machine. Or 4, depending on how you want to define things. It turns out that solenoids powered by DC can be stronger than AC powered ones, and Williams began tinkering with them around this time. Only the pop bumpers and slingshots are powered through the rectifier though, as you can see in the schematic. Everything else, including the flippers, is powered by 24 volts AC. And why don't we talk about the flippers? As with pretty much everything that moves, they're powered by a solenoid. But in this case, they're controlled by the player with buttons on the sides of the cabinet. Those buttons simply push the contacts of a leaf switch together, which sends power to the flipper coils. Then they pull on a linkage and the flipper bat pops up. Flipper coils, though, are unique. See, a strong solenoid needs quite a lot of power. That means they get hot over time. For every other solenoid in the machine, that's not much of a problem because they're only activated in short bursts. But the flippers are controlled by the player, and that player might just want to hold the flippers up in order to catch the ball. That could cause the coils to overheat, and coils that overheat tend to get melty, then smoky, and on rare occasions, fiery. Slow blow fuses throughout the cabinet should prevent a serious problem like a fire in the event that a coil becomes locked on, which can happen, but we want the flippers to be able to stay up without causing any trouble. So, if you look carefully at the flipper coil, you'll see that it has 3 terminals. The long coil of wire that actually makes the solenoid has a connection in its middle, which allows it to function at 2 power levels. When the flipper is at rest, the button sends power to the coil through the center tap. This bypasses half of the coil's length, reducing the number of turns of wire that current flows through, which makes the solenoid more powerful. That might seem backwards, but that's just how solenoids work. But once it reaches the end of its travel, it opens this switch, another end of stroke switch. That removes power from the center tap, meaning current must now travel through the entire length of the solenoid wire. This reduces the current flowing through and the strength of the solenoid, and allows it to stay energized without burning up. And for a demonstration of this principle, observe the change in sound as I force the flipper bat down while holding in the button. The lights in the machine even dim while I do this. It's a lot of current. At this point, we've looked at how everything on the playfield works, we've seen how the machine shows you your score, and we've seen how points get added to it. But the machine is doing a heck of a lot more than simply adding point values together, which you might have been able to tell by all the stuff inside. There are layers and layers of complexity built atop the basic scoring functions. For instance, the machine has to know how to count. You get 3 balls per game, and then it ends. It also needs to know how many players there are and change which set of score reels is active after each ball. But also not do that if the current player scored an extra ball and gets to shoot again. Then there's the bonus ladder I referenced earlier, which always starts at 5,000 points, but can be advanced when you hit certain targets in increments of 5,000. And I think that's a good place to move to next. The number 5. Here, watch this. How on earth do you suppose that happened? I hit a switch just once, but the score reel moved 5 times, all on its own. Well, remember that ticking it was doing in the beginning? Perhaps you noticed it happened in groups of 5. Listen again. Turns out the number 5 appears all over the place. This target is worth 500 points, this lane scores 5,000, as does the kickback target. The bonus values increment in steps of 5,000 points. And then there's this thing's name, Aztec. That has 5 letters in it, and some of the targets will award points based on how many of those 5 letters are lit. How is it doing all that? And why does everything happen in 5s? Well, it's time I introduce you to the score motor. This wonky looking contraption is the closest thing this machine has to a central processing unit. The score motor consists of an electric motor which, through a speed reduction gearbox, slowly rotates a series of 8 cams, upon which rest a ridiculous number of switches in 8 stacks. The stacks, from left to right, are called index, 1, 2, 3, 4, 5, impulse, and impulse forward. Incidentally, impulse forward just has a single switch, which is used only in the reset sequence. Ah, sequence. What a good word. That is pretty much the whole idea of the score motor. It allows things to happen automatically in a sequence. On every one of the 8 cams, there are a series of divots or bumps. These will actuate the switch stacks as the cam rotates. Either the stack will briefly fall into the divot and the switches within will make or break contact as they move, or, in the case of the 2 impulse cams at the far right, a series of bumps will push up on the switch stack, which accomplishes the same thing. The cams 1 through 5 are all offset such that the switches they actuate will be bumped in sequence, 1, 2, 3, 4, 5. And impulse and impulse forward are bumped 5 times with every rotation. The index cam on the far left is critical for the score motor's functions. The switch on the top of this stack is the motor run switch. It's much like the self-powering interlocks we've been looking at in other relays. When closed, it provides power to the motor and thus it will run. And crucially, that switch is closed whenever the motor is out of its parked position. Once it gets back to the parked position, the switch stack falls into the divot, that switch opens, and the motor stops. In practice, this means that if anything should cause the motor to start moving, it will keep itself moving until it's made a complete cycle. It even works if I just push on it. But you'll notice that when I did that, nothing happened. This is what's both very confusing and completely critical to understand about electromechanical systems like this. With the exception of the motor run switch, the rest of these switches aren't connected to anything, even when the game is on and in play. They're just there, clicking away without accomplishing a thing because the wires they're connected to hit dead ends. It takes 2 to tango, and to make something happen, the machine performs a dance where it constantly rewires itself on the fly. And what does it use to make that happen? That's right, relays. That's why there are so many of them in this machine. To actually make something occur, you need a relay to connect these bouncing switches to other things in the machine. That way they'll, do stuff. Take this rollover worth 5,000 points as an example. You'll never guess what the 5,000 point rollover switch completes a circuit to. It's none other than the 5,000 point relay, which lives on the underside of the playfield. This relay has 3 switch contacts, which all connect to the score motor. The switch on the right sends power to the motor to start it turning, which you can observe when I bridge the contacts. The switch on the left is yet another relay interlock. The rollover switch is what sends the initial power to the relay coil to energize it, but once these contacts are touching, the relay keeps itself powered. If I bridge these contacts, you'll see the relay pull in and lock itself on. If this feels familiar, well, it's doing the same thing as the switches on the points relays in the back box. It keeps the relay energized until its task is actually complete. And right now, I've disabled the score motor. Since it's not moving, this relay cannot complete its task, and the machine is locked up in this state. Its task, remember, is to add 5,000 points to the score. And the middle contact in the relay is what makes that possible. When closed, this connects the 1,000 point relay in the back box to this switch on the top of the impulse cam of the score motor. When I plug the score motor back in, the cams begin rotating, and since the impulse cam actuates its switch stack 5 times, the 1,000 point relay will receive 5 pulses through this switch. And right after it sends the 5th pulse, the relay lets go. That's because the relay's interlock is connected through a normally closed switch on cam 5. Once cam 5 is actuated, that switch is broken, so the relay releases. And now the machine is at rest. This happens very quickly, which is incidentally the point, so it's kind of hard to keep track of. However, I can slowly rotate the score motor by hand so we can observe each individual action occur. Once the 5,000 point relay becomes energized, it locks on by keeping itself powered through a switch on cam 5. It also connects the impulse switch through to the 1,000 point relay. As I turn this, we hear the machine dinging and buzzing every time this switch stack pops up. But the relay's still locked on because cam 5 hasn't been actuated yet. When that switch stack falls into the divot, we hear a click as the relay loses power and lets go. As you can imagine, the timing here is critical, and the cams are aligned so that the 5th bump of the impulse switch happens just before cam 5 actuates its switches, which also happens just before we get back to the start point and the index switch actuates. With the score motor re-enabled, this happens quickly and automatically. I hope you can appreciate how amazingly bonkers this is. And that was one of the simplest relays in the machine, causing it to do one of the simplest automated tasks it can do. We've still got a bajillion relays to look at, plus a solid 32 other switches in the score motor. And we're how long into this video? Yeah, I can't cover how everything works in this machine, let alone in a single go. So there will definitely be a second part. But before we conclude here, let's talk about the Aztec targets, how they light up their respective letters, and why that changes what other targets do. By now, I hope you know what the switches in these targets send power to. Say it with me now, relays. And Williams was kind enough to mount them in order on this support below the playfield. Here's the A relay, the Z relay, the T relay, the E relay, and the C relay. For now, let's just focus on the A relay. This single relay features all 3 kinds of switch contacts. The 3 leftmost switches are normally open, and as the relay pulls on its armature, the contacts are pushed together. Then we have a normally closed switch. This one does just the opposite. But the 2 on the right are make-break switches. The relay moves the center blade, and instead of turning something on or off, it redirects the flow of power from one place to another. Like the 5,000 point relay we just looked at, this relay will power itself once it has been actuated. As soon as the left-hand switch makes contact, it provides a power bypass and the relay becomes locked on. And this relay will stay locked on until the end of the ball in play. The next 3 switches have to do with the center target and the kickback lane. I'll get back to those in a moment. The 2 switches on the end, the make-break switches, change the machine's behavior and appearance once the A target has been hit. The A rollover lane is marked Lights A, 1000, and Lights Spinning Target. Obviously, that means it lights some things up, but it also makes this light go out. It's this make-break switch that changes which lights are lit. Before I hit the target, 6 volts was sent to the right-hand contact, which illuminated the lamp above the lane. But once I hit it and the relay locked on, power was redirected to the contact on the left, which leads to the 2 A lamps as well as the spinner. Lighting the spinner target changed its point value from 100 to 1000 points. How? Well, that's what the other make-break switch did. It disconnected the spinner from the 100-point relay and connected it instead to the 1000-point relay. Now, I could just tell you that, but you might have noticed that the wires in this machine are color-coded, so you can trace where they go. Let's follow their path. This is the spinning target switch. When closed, it sends power out this gray wire with a red stripe. It ends up bundled in the harness and comes back out right here at the relay. There, it's sent out either through the white wire with a red trace on the right, or the brown wire with a yellow trace on the left. Those wires re-enter the harness, split out towards the back into this small bundle that's connected through a Jones plug to the back box, and sure enough, those 2 wires eventually end up at the coils of the 100 and 1000 point relays. Which one is connected depends on whether or not the relay is energized. And here's what it looks like on the schematic. Power is sent through the spinner switch on the gray and red wire. That ends up at the make-break switch in the A relay. The normally closed contact connects over to the 100-point relay, so the spinning switch will send power there when closed. But when the A relay is energized, power is redirected to the brown and yellow wire, which connects up to the 1000-point relay. But the spinning target is only one of 3 targets that the A relay will change in value. There's also the center target and the kickback lane. Those targets are worth a set value when none of the letters are lit, but if even a single letter is lit, they're worth more points. In fact, more for every letter that's lit. In the case of the center target, it's 1000 points for each lit letter, and the kickback lane awards 10,000 points for each lit letter. That means that, technically, the targets have 6 possible values each. How can this sort of circuitry possibly manage that? Well, it's actually simpler than it might seem. Let's look at the center target first. The center target switch sends power to the center target relay, of course, which is similar to the 5000-point relay we looked at earlier. Once powered, it locks itself on, starts the score motor spinning, hooks the 100-point relay up to the impulse switch on the score motor, and releases just after the 5th pulse of the 100-point relay. Thus, it adds 500 points to the score. But look at the circuit path on the schematic. Power comes through the impulse switch here, then we have to follow a gray and white wire down to B19. Here it is, and then it has to go through all of these normally closed switches before it makes it to the 100-point relay. If they're all closed, then we're fine. The 100-point relay will be pulsed 5 times, and we get those 500 points added to the score. But if any one of the Aztec letter targets has been hit, its respective switch in its relay is open, and since all those switches are wired in series, this circuit path is broken, so it no longer works. But we get 1000 points for every letter that's lit. And we just have to move a little ways up on the schematic to see how that works. Here again we see switches in the A, Z, T, E, and C relays. These are normally open, but close when their respective relay is energized. And right above them, we see switches in a circle. This is how the schematic tells us those are in the score motor. And the notation tells us where in the score motor those switches are. The A relay is connected through the index stack switch B. That's the second switch from the bottom. The Z relay through stack 1, switch A, the bottom switch in the stack. The T relay through switch stack 2, switch A. The E relay through stack 3, switch A. And the C relay through stack 4, switch A. We already know that those switch stacks are actuated by the score motor one at a time in order. So you can imagine what's happening here as a sort of scanning sequence. When the center target is hit and its relay is energized, each of the letter relays receives a pulse of power at their respective switches. The A relay receives its pulse immediately, as it's connected through a normally closed switch at the index position. But as the motor turns, that switch opens, and then the following relays get pulsed one at a time. Whichever relays are energized will have this switch closed, so its respective pulse makes its way through the center target relay and to the 1000 point relay coil. Thus, it adds 1000 points for every lit letter. This is pretty wild, right? Despite just being a tangled mess of wires, relays, switches, a motor, and some cams, we have a machine which methodically checks whether each of the 5-letter targets has been hit and awards points if it has been. This results in a unique pattern of dings depending on which targets are lit. I won't waste your time any further by going through every possible combination, but here are a few. You probably noticed that right alongside the center target relay in the schematic was the shooter relay. That's what I've been calling the kickback lane. Williams decided to refer to this as the shooter, which is very confusing since, you know, this is also the shooter. But anyway, that target works in essentially the exact same way as the center target, but it pulses the 1000 point relay through the impulse switch when no letters are lit, thus awarding 5000 points, and pulses the 10,000 point relay for every lit letter. The only other difference is that the shooter coil gets fired at the end of the sequence through switch 4E in the score motor to kick the ball back out of the target. While I covered a lot of what this machine does in this video, it's probably pretty obvious based on all the other stuff in here that there's a lot more to see. In part 2, we'll take a look at how the machine manages to do some of its more complex automated sequences, like this one. Yep, it added 25,000 points to the score all on its own, then changed the ball in play light from 1 to 2. Apparently, it can count, and it also knows your score. Cross 350,000 points and you've won a replay. Stay tuned for how that all works. It's just as nuts as everything you saw here. Thank you very much for watching. I hope you enjoyed it and that I've been able to help you understand all this nonsense. The thing is though, it's not nonsense, it's logic. And that's part of why I like machines like this so much. You can actually look at them, pick it apart, and understand what it's doing and why. It blows my mind how folks of the past figured all this out and got these things manufactured in mass. And perhaps even more mind-blowing, while this machine is from 1976, most of the tech in here existed in some form back in the 1930s. It just got built up in layer after layer until we arrived at this. And to be honest, this machine isn't that complex. There are plenty of electromechanical pins out there which have much deeper rule sets and many more targets. In fact, 20 years prior to this one getting manufactured, Bally introduced a game with multi-ball. Yeah. Maybe one day we can take a look at a more complex machine, but for now, I need to go to bed. Good night, everybody. You didn't know this, but I'm even wearing PJs. You never know what I've got on below the desk or behind the pinball. In fact, 10 copies. Slightly. Ooh, the left-handed teleprompter control is gonna throw me off. I'm just gonna need to pick this up. Quite the assortment of weird we can slide the glass out and the playfield will simply lift right up. I botched the word simply. And just a bit, I promised. Promised? That's not the what? Large rings may be stretched across 2 or more posts to create a linear barrier, but sometimes that sounds weird and I'm gonna start over. But you'll find plenty of individual rings with their own rings too. Well, this line's not going great. And that advances the mechanism by 1 step. Or it would if I weren't so clumsy.